So we are back for part 2 of module 3, and in part 1 of module 3 we ended on looking at how we can use a graphical form to find work boundary. And now we're going to shift to the second methodology which we had talked about, which is to use an analytical relationship between pressure and volume and actually solving it through an equation. And one way to do this, and the most popular way for in thermodynamics to solve processes using an equation, is to use an equation for the polytropic process. And what a polytropic process is a process that can happen with gases where we can use that equation to solve for the work boundary. And in gases, typically when we have a PV diagram from 1 to 2 with our piston expanding, for example, instead of having a straight line or something like that, we might have a line that looks something like this for the process from 1 to 2. Okay, and obviously finding the area under the curve of this line is not as easy as our previous examples. So the polytropic process is an example of an analytical, where we can find an analytical relation between P and V. And this relationship may be described, so the polytropic process may be described as PV to the power of n is equal to a constant. So that's our equation for polytropic process. And n is also equal to a constant. And this n varies. So this n can vary depending on the gas that we use and can vary depending on the process that we use. Okay, and it's going to be pretty interesting. So how do we solve for work boundary using this equation? Well, we know that work boundary is equal to the integral of P dV from 1 to 2. Okay, in our process, the work boundary is the area under the curve, which mathematically means that it's the integral of P dV from 1 to 2. So if we take our equation of PV to the n is equal to a constant, and I'll write the constant as C now, we can actually come up with a relation to substitute P in the top equation. So we can put P on one side and then solve for the work boundary. So if we put P on one side, we now have P as a function of V. So it's going to be C over V to the n. And we can rewrite that as P is equal to C times V to the negative n. Okay, it's just the same expression, just with a power of negative n, so everything is on top. And now what we can do is we can substitute this for our P here, and now we have a relation that can be solvable, an integral that's actually solvable. So we have work boundary is equal to the integral from 1 to 2 of P dV, which is equal to the integral from 1 to 2 of C V to the negative n dV. And if we actually solve for this equation, so if we solve the actual integral, you would get that this is equal to C V to the minus n plus 1 over minus n plus 1. Okay, this is a simple rule of integration. Hopefully you remember your integrations, and this would be from 1 to 2. And now we can put the values in. So we would have C times V2 to the minus n plus 1 minus V1 minus n plus 1 divided by minus n plus 1. That would be our equation. And now we also know that since PV to the n is equal to a constant, so going back to our equation of PVN is equal to constant, So I'll write it fully. We can say that if our process follows a polytropic process, as shown up here, so if the process is following a polytropic process, then we can say it means that P1 V1 to the n is equal to P2 V2 to the n, because at any point in the process should be equal to a constant. Okay, any point on this line should be equal to a constant. So we can say that P1 V1 to the n is equal to P2 V2 to the n. And so now we can substitute, so we can say that C is equal to P1 V1 to the n, and it's also equal to P2 V2 to the n. So now what we can do is we can substitute that into our equation for C. And so we get that this equation at the top would now be equal to, and I'm going to substitute P2 V2 to the n into here, okay, for this C. And I'm going to say that P2 V2 to the n multiplied by V2 to the minus n plus 1 minus, and I'm going to do for the second term, so for the first term I'm going to use P1 V1 to the n, and for the second term I'm going to use, for the first term I'm going to use P2 V2 to the n, and for the second term I'm going to use P1 V1 to the n, right? This is equal to C. So we can use both terms. So I'm going to do P1 V1 to the n, it's the same value as P2 V2 to the n, multiplied by V minus n plus 1. Okay, hopefully this makes sense mathematically. If it doesn't, take a minute to try and understand what's happening. Okay, now that we have those two, what happens to our powers of V? So what happens to the sum of the powers here and here? If you have two V's together and they're both to the power of something, we can just add the powers together. And we end up with n minus n plus 1. N minus n plus 1 is equal to 1. So we end up with an equation that says, and sorry, I forgot to put the minus n plus 1 over here on the bottom. Okay, so we get that the integral of PDV is now equal to P2 V2 to the power of 1, so it's just V2, minus P1 V1 divided by 1 minus n, or minus n plus 1. So from the polytropic process, we can say that work boundary is equal to P2 V2 minus P1 V1 over 1 minus n. Becomes a very simple equation that we can use. So if we're told we have a polytropic process, we can go ahead and say, in a question, let's say we're told that there's a polytropic process, use it for this gas with an n is equal to a certain value. Then if you're given P1, V1, and V2, for example, you would be able to find P2, or you'd be able to find work boundary as well. Okay, so that's pretty interesting. And if you're using an ideal gas, you can combine this equation with PV is equal to MRT to use it for an ideal gas. So if you need to find out some terms, you can use ideal gas. And that means that we can actually do something clever here. We can also say that work boundary, so I'm going to write for ideal gas, because this is only for ideal gas. Okay, we have work boundary. We can substitute MRT into our system. So we would have MRT2 minus MRT1 over 1 minus n, which we can simplify to MRT2 minus T1 over 1 minus n. Okay, so that's only for ideal gas. So this part is only for if you're told you have an ideal gas, or if you assume ideal gas, you would have this equation right here. Okay? So now, what happens if n is equal to 1? What happens if n is equal to 1 to our above equation? We have work boundary as P2V2 minus P1V1. If n is equal to 1, we have a problem, right? Our 1 minus n becomes 0, and you cannot divide by 0, so you cannot find the work boundary for if n is equal to 1. So we actually have to redo a process if n is equal to 1. So what we can say is that if n is not equal to 1, so if we know that n is not equal to 1, we can say that work boundary is equal to the integral from 1 to 2 of p dv, which is equal to p2 v2 minus p1 v1 over 1 minus n. Now, if n is equal to 1, we sort of have to restart the problem. If n is equal to 1, we can now say that pv to the n is just equal to pv, and that's a constant. So we know pv is a constant. Okay, it's just pv because n is equal to 1. And so now we can solve our equation again, but now we have to solve it in terms of our new sort of simplified equation without the n being in it. So we have P1V1 is equal to P2V2, which is equal to a constant. And in this case, the integral of PdV, and I'll go a little bit faster through this integral, but you can definitely take the time to understand it. But the integral of PdV would be equal to P1V1, which is our constant, our C, okay, times the integral from 1 to 2 of dv over v. Okay, so we have dv over v. Because we know from this equation right here, we know that from this equation, we would get, by rearranging, we would get that P is equal to C over V. Okay, and we can use C as either P1V1 or P2V2, so we're going to use P1V1. And the integral of dv over v, as you all know, is the natural log of v over v. So we're going to get natural log of v, essentially. So the integral from 1 to 2 of p dv, in this case with n is equal to 1, is equal to p1 v1 natural log of v2 over v1. And this is work boundary, and this is for a polytropic process with n is equal to 1. So just making sure that we know that this is for n is equal to 1, and we know that this equation right here is for n is not equal to 1. So there's two different equations depending on what n is equal to. Okay. Now, these two expressions that we came up with of the integral of PdV may or may not equal to work boundary. Okay, so it depends on the thermodynamic analysis. So if the thermodynamic path does not look like a polytropic process, then you can't use the polytropic process equation. You will be told in a question if you have a polytropic process or not. You will usually be told. Okay, there's one exception to this, but we're going to be doing an example on that in a little bit of time. So we'll have an example either in part 2 or part 3 where we will be discussing this issue at hand. So the next thing I want to do is start to do some examples. And we're going to do some mixed examples between polytropic process and non-polytropic process. So we're going to be looking at both of them sort of at the same time. Okay, and all these questions are in your handout, so if you want to copy over the questions from your handout, you can. Okay, so it's up to you, but I'm going to copy over the questions as well here. Okay, so I'm going to copy over the first example that we're going to do. And we're really going to go through the whole process. Okay, so we're given a problem where we have a piston cylinder device with a set of stops initially contains 0.6 kilograms of steam. So the first thing I like to do is to sort of read the question and highlight some points. So we know that the problem has stops. We know that it has 0.6 kilograms of steam. Okay, so what does steam mean? Steam means usually boiling water. Okay, so that means that it's usually, I wouldn't write boiling water actually. Let me just rewrite it. Let me write it. It's going to be vapor or gas. Okay, this is sort of a hint, but we can still check with our tables if we have a vapor or a gas in that case. And we're told that the 0.6 kilograms of steam are at 1 megapascals in 400 degrees. This first sentence determines our first state. So what we're going to do in this case is we know that this is state 1. Okay, and we're going to work through so that we can understand what's happening and how we're going to set up our problem. So this is going to be a good measure of how we work with our information and sort of figure out what the different states are, just like we were doing in the previous module. So then we're told that the location of the stops corresponds to 40% of the initial volume. So we're told that the stops are 40% of the initial volume. Okay, and then now the steam is cooled. So the first question is determine the compression work if the final state is 1 megapascal and 250 degrees. And then a second step where we have 500 kilopascals and then determine the final temperature. So the first thing I'm going to do in this problem is to define my states. Okay? And you can define those states you can write them on the right side, you can write them wherever. For the first part of the problem, what I'm going to do is I'm going to write my states directly in the white box so that we have them there. So we know that our first state is defined by the first sentence, and luckily it's also shown in our figure. So let's write what the first state is. So the first state says that P1 is equal to 1 megapascal. Okay, and we're also told that T1 is equal to 400 degrees Celsius. So the first step in figuring out our problem is to define state 1 and state 2. Okay, so state 1 is defined, I'll write state 1 here. Okay, state 1 is defined by everything that's happening at state 1. So we have a mass of 1, which is equal to 0.6 kilograms, and that's all the information that we're given in state 1. Now in state 2, we're told, and this is the final state, we're told that pressure 2 is equal to 1 megapascal. Okay, so still the same pressure. And we're told that temperature 2 now is equal to 250 degrees. So the pressure has not changed. This is a constant pressure process. And we're also told, that's what we're told. Now, do we have any other information? Yes, we actually do, right? We have other information. We're told that the mass, does the mass change between our two states? No, the mass is trapped. The mass of the steam is trapped. So M2 is equal to M1, which is also equal to 0.6 kilograms. The mass does not change. And we're told one more information. We're told that the volume at the stops is equal to 40% of the initial volume. So the volume at the stops is equal to 0.4 times V1. So we don't know what V1 is. So let's just write, we have V1 here and we don't know what it is. And we also don't know V2 in this case. Okay, so we have to try and find V1 and V2. And we'll see why we have to try and find it in a second. Okay. So first things first, let's try and understand the problem. So we're told to find the compression work. So we know that it's going to be a compression. Okay, so on our PV diagram, we're going to have a compression. And obviously, the problem tells us that we have steam. It doesn't tell us that it's a polytropic process. Therefore, we have to find work boundary is equal to the integral from 1 to 2 of PdV. We have to find the area under the curve. Okay, so we're going to have to find the area under the curve. So that means that we need to have some sort of PV diagram in order to figure it out. And in this case, we know that from pressure 1 to pressure 2, we have the same pressure. So the pressure stays constant between state 1 and state 2. So it's going to be pretty simple. Okay, we know that P2 is equal to P1. Therefore, we're going to start somewhere at a high volume, okay, where the steam is hot, and then it says the steam is going to be cooled. So we're going to start at a volume, for example here, of V1 and pressure of 1 megapascal. So that would be 0.1. And then our 0.2 is going to be somewhere to the left where we have still a pressure of 1 megapascal, but now we have a different volume. So essentially, we have to find the area under this curve to find the work boundary. And in order to find the area, we already have the pressure, right? So our work boundary, in this case, in this kind of shape, is just the area. So it's P1 minus 0 multiplied by V2 minus V1. And so what we need to find is essentially V2 and V1. So how are we going to find V2 and V1? How can we find volume 2 and volume 1? So that's a question that I'm asking you right now. So in order to find V2 and V1, we're going to have to complete our state 1 and state 2. So if you remember, if we have two different points in the state, we can find the third one. Okay, we have pressure and temperature, so we can find the third one. And the third one is actually not going to be volume, but it's going to be specific volume. So we're going to be able to find specific volume at both points. And are we going to find specific volume? Are we going to find specific volume using ideal gas equation or using our tables? Since we have steam and steam is water, we're going to be using our tables. So I'm going to write using our tables, we find V1 and V2. And from V1 and V2, we can find V1 and V2. Remember, V is equal to M times little v. We have mass, so we just have to find V, and then we'll just have to find specific volume, and then we'll be able to find the actual volume to plug into our equation. Okay, so we're going to go to our tables. And for this system, we have tables for steam. So at state 1, we're told that we have pressure 1 is equal to 1 megapascal, and temperature 1 is equal to 400 degrees Celsius. And from this, from tables, we're going to find V1. So what table are we going to use? Well, we're going to start by going to table A4, A5. Okay, we have pressure and temperature, so we can go either to A4 or to A5. I like to go to table A5 because it's the pressure table and it gives us the saturation temperature. So if we go to the pressure table, We have 1 megapascal, which is 1,000 kilopascals. So it's right here. So it's a table for water. So the first step is we go to table A5. We find that our pressure, and following our pressure, we're given the saturation temperature. Okay, so we're given 179.88, and I'm going to go through all the steps of this for now. Later on in the semester, I'm going to go through less of the steps of finding the tables because you'll become very, very good at using tables to find values. Okay, so right now it might seem like a challenge during the semester, but it'll get easier as you go along. Okay, so we have a saturation temperature. So from table A5, we have Tsat is equal to 179.88 degrees Celsius. Okay, and since we have 179.88, we see that T1 is greater than Tsat. So what does that mean about our system? It means that the temperature is above the boiling point of water at that pressure. And therefore, what we can say is that we have a superheated vapor. Since we have a superheated vapor, we're going to go to superheated vapor tables to try and find V1. So we now go to our table A6, which is our superheated vapor table, and we're going to look for 1 megapascal. So we're going to look for 1 megapascal. We have here the box for 1 megapascal. And now we know that our temperature is 400 degrees. So our volume is going to be this value right here, 0.30661. So V1, little v1, is going to be equal to 0.30661 meters cubed per kilogram. And we're going to do the same thing for P2 and T2. But now we're going to go a little bit faster. Okay, we have the same pressure, 1 megapascal, we have the same pressure, and we have the same temperature. We have a different temperature, 250 degrees. Now this temperature is still above Tsat. T2 is still greater than Tsat, so we're still in the vapor form. So since we're still in the vapor form, in the superheated vapor form, we can go to the same table and find V2 at 250 degrees Celsius. So if we go back to this table, we can now go to 250 degrees Celsius and find that our V2 would be equal to 0.23275. So V2 is equal to 0.23275 meters cubed per kilogram. So now that we have V1 and V2, we can find the actual volume by multiplying by M. So I'm going to write it on the top left here. So we're going to have V1 is equal to M little v1, and V2 is equal to M times little v2. And we get that volume 1, if you do the math correctly, is 0.184 meters cubed, and V2 is equal to 0.140 meters cubed. And so now we have all the information available for us to solve the problem. We know that work boundary is equal to P1 minus 0 times V2 minus V1. So we can now plug back into this equation, and we can say that work boundary is equal to P1, okay, so 1,000 kilopascals, multiplied by V2 minus V1, which is 0.184 meters cubed minus 0.14 meters cubed. And so we get a work boundary that is equal to negative 44.3 kilojoules. Okay, because we're using kilopascals, we get kilojoules. Okay. Now, in the question, it says to determine the compression work. So in the question, it says to determine the compression work. And when you're asked to determine the compression work, you don't really, so we see that the work is negative. And that makes sense because we have compression, right? We have work on the system. Now, if a question asks you for compressive work, which I won't really ask you in any exams or quizzes, but if it asks you for the compressive work, you can also write work of compression. So just the work of compression, not the boundary work. You could say that the work of compression is equal to negative boundary work. Okay, so boundary work is always assumed to be negative when you have a compression, and compressive work is just the opposite of boundary work. So you could say that work compression is 44.3 kilojoules. But for me, this is the correct answer. This is just, the book is asking you for compression work, and sometimes they might ask you some questions where you ask for the compression work, in which case you would just put the positive of that, but that's not really always useful. Now, we now have solved the first part of the question, okay, with this answer right here. So let's go to part B. And part B complicates things a little bit because we're told that in part B, we now have a new point 2, which is called P2 is equal to 500 kilopascals. So we're told that the final pressure is equal to 500 kilopascals. And we know that initially, if we look at our system, our piston cylinder assembly, we know that initially our piston was somewhere here. Okay, we had this point right here initially. And I'll put the stops right there. Okay, and then in a second instance, we were told that this piston started moving down, and we know that because V2 is less than V1, so V2 was equal, volume 2 was equal to 0.140, and this was equal to 0.184. V1 was equal to 0.184. So we know that it went down by a certain amount. Okay, so in the previous part, we know that it went down a certain amount. Now we're told that pressure 2 is lower than 1,000 megapascals. So how is that possible? Lower than 1 megapascal. So now how is that possible? How can we lower the pressure? How can pressure be less? Pressure is less if you hit the stops. If you hit the stops, the pressure can go down from 1 megapascal. If the piston does not hit the stops, then there is no way that you can change the pressure in your system. Okay, except if you added some pressure from the outside by adding weights or something like this. So we actually have, our piston actually moves down to this position in this part of the question. So P2 is equal to 500 kilopascals means that our piston has moved all the way to the stops because the pressure has changed. Okay, this is a rule you have to remember. If the stops were above and the piston was moving up, you would get the same exact thing, except the pressure would start increasing once you hit the stops. Okay, we did some examples in part 1 to describe that as well. Okay, that's very important to understand. So we can rewrite our steps essentially for this problem as state 1 and state 2 once again. So we have state 1 is equal, so state 1, sorry. And for state 1, we still have P1 is equal to 1,000 kilopascals or 1 megapascal. Temperature 1 is equal to 400 degrees Celsius. And we know V1 already. We know that V1 is 0.30661. We also know V1 is equal to, just let me check the number again, is equal to 0.184 meters cubed. And we also have the mass, which is equal to 0.6 kilograms. And now, at our new state 2, we now are told that pressure 2 is equal to 500 kilopascals. And we're told that since we know our pressure 2 and we know the fact that the piston has hit the stops, what does that mean about volume 2? What is volume 2 equal to if we know that our piston has hit the stops? Well, we were told that V stops in the question is equal to 0.4 times V1. So that means that V2 is equal, since we know that V2 is equal to V stops, we know that V2 is equal to 0.4 times 0.184. And we're going to actually leave it in this format right here. So we're going to say that V2 is just equal to 0.4 times V1, and we'll see why. So we're just going to leave it as V2 is equal to 0.4 times V1, essentially. Okay, and we'll look at how we can use that. Now, what that also means is that little v2 is equal to 0.4 multiplied by 0.30661. Right? It's the same exact equation. We just get rid of the mass and it's the same equation. So we can say that v stops is equal to 0.4 times v1, but we can also say that little v stops is equal to 0.4 times little v1. It's the same exact thing. The mass doesn't change. And we get that v2 is equal to 0.1226 meters cubed per kilogram. Okay, so now we have a little volume 2, and we can now figure out what temperature 2 would be. But we don't really need temperature for part B, right? We're not told what part B is, and we don't really need temperature. Now, let's go back to part B for a second. So this we'll use as reference now for our states. And let's go back to the question in part B. The question in part B asks us for the work boundary. So I'm going to go slightly down. So it asks us for the work boundary, which is the area under the curve. So it's integral from 1 to 2 of PdV, which is the area. And if we draw a PV diagram now, we have our PV diagram, and we know that the piston moved all the way down to the stops. So if we draw our PV diagram, we started with state 1 at volume 1, and we moved along a line of constant pressure up until we reached the stops. So this is equal to V stops. Once we hit V stops, what happened to our pressure? Our pressure started going down because our piston couldn't go down anymore. So our PV diagram actually looks something like this for this system. And point 2 is right here at 500 kilopascals. And this is 1 megapascal or 1000 kilopascals. Okay, so up until we reach the stops, the pressure did not change. Once we reach the stops, the pressure started going down. So this would be our PV diagram. Now, in order to find the work, this part, and we're going to call this little point 1b, just so we have it as a different value than 1 or 2. And we see that from 1B to 2, there's no work being done. There's no area under the curve because nothing is moving, right? The piston is not moving anymore once it hits the stops. So the work from state 1 to state 2 is just the area under this. And so we're going to write this area out. We're going to say that it's equal to P1 minus 0. Okay, it's the whole area, P1 minus 0, multiplied by V2 minus V1. In this case, we now know that V2 is equal to V stops. And V stops is equal to 0.4 V1. So it's 0.4 V1 minus V1. That's why we didn't need to solve for V2. You could have solved for V2 and then just plugged in the values. It would have been fine too. So we get that work boundary, if you plug in the values for everything, you get that work boundary is equal to minus 110.4 kilojoules. And you can once again write that the work of compression is just a positive 110.4, but that's not necessary. Okay, I like this answer better for the question. So work boundary is equal to minus 110.4 kilojoules. Okay, so now part C asks us to find our temperature. So this is part C, finding our temperature. So how do we go about finding our temperature? Well, it's very easy. We know that volume 2, specific volume 2 is 0.1226, and we know pressure 2 is 500 kilopascals. So let's try and find temperature 2. Temperature 2 is just equal, so temperature 2, how do we find it? We go to our tables. And we have, from our tables, we have that we now have P2 is equal to 500 kilopascals, and V2 is equal to 0.1226 meters cubed per kilogram. So we're going to go to our tables, and we're going to start with table A5 again, because now we're not sure if it's a superheated vapor or not. We're now at a new step, so we're now at a new pressure and new volume, so we need to start over. So we're going to go to table A5. And in table A5, we're going to look for 500 kilopascals, which is right here. Okay, so this is our value. And we see that our temperature of saturation is 151.83. And we know that our VF and our VG are these two values right here. So I'm going to write this directly here on the table so it's easier to see. But we know that V2 is equal to 0.1226. Okay? And we're given VF as 0. So VF is equal to 0.001093. And we're given that VG is equal to 0.37483. So we can clearly see that V2 is between VF and VG. So what does that mean? That means that our fluid is a saturated mix. And if it is a saturated mix, that means that it's currently a mix of steam and liquid water. And what does that mean? That means that saturation, remember, means that it's currently boiling, or the opposite in this case, because we're cooling it down, so it's in the boiling phase or the cooling down phase where it gets back to liquid water. Okay, and that means that our temperature is actually equal to the temperature of saturation. Okay, so we remember in the saturated mix phase, the temperature does not change. The temperature stays constant. Therefore, our temperature is T saturated, which is 151.83 degrees Celsius. So we can go back to our question and say that from table A5, we had a sat mix, and due to that saturated mix, we have T2 is equal to 151.83 degrees Celsius. And that concludes our first big example for this chapter, looking at how we can find work boundary for 3 different states. And this problem is actually pretty complicated because we have stops involved in it, and we see that in part B we actually had 2 steps from 1 to 1B and then 1B to 2. And I think it's always very important to be able to draw the diagram for what is happening. And you can refer back to the list that we had developed in part 1 in order to do so. So we're going to stop part 2 here, and then in part 3 we're going to continue with example problems on polytropic processes and some special cases as well.